We're back in the shack today. Let's model a simple antenna using EZNEC. Okay, this is just going to be an introduction to modeling antennas with EZNEC. And I'll start with the absolute simplest antenna that you can model. There isn't any antenna simpler than this one. And it's just a horizontal dipole. So I just picked some random numbers here, and this one should be resonant on 40 meters. We can check that, but you can see that I've just got a wire in the air, 38 feet, that's about 70 feet long. So the wire's about 70 feet long. It's 38 feet off the ground. And looks like I'm using number 11 wire. I don't know why I'm using that. Let's change that to 14, number 14 wire. And real quick, we'll just check the SWR on it. Let's go from 7 to 7.4 should work. We'll run that. And as you can see, for 50 ohm use, we're a little long. So let's go ahead and shorten it just a little bit. Let's make it 68 feet. Still a little bit long. 66 feet. There we go. That's about what we're looking for. So our low point here is 7.19 megahertz. That's about perfect for 40 meter use. So how did I get here? Well, let's start over. So what we want to do is we're going to start out in free space mode. And let's change our height by 38. Let's take it down to 0 feet. So we're going to put this right on the ground. And now this is a free space wire that's 66 feet long. We have no ground to worry about. And if we model that, you can see it's very similar to what we had before because we were up 38 feet, which is pretty good for a 40 meter antenna. But you can see we're at right about 70 ohms, 71.71 ohms, which is typical of a straight dipole. Straight dipoles usually end up about 73-ish ohms is where you would expect to see one of those. So you can model these antennas. Let me get it on the right frequency here. And we'll hit FF plot. And since it's in free space, you can see this is just a big ball of RF. We have some nulls, but because there's no ground reference, it's just a big ball of RF. So that's basically as simple as it gets. Now, our ultimate goal today is to model a ground plane antenna. And a ground plane is a vertical. So let's flip this around and make it a vertical. And to do that, all we're going to do is just take our y-axis and turn it into a z-axis. So z at 0 feet, we're going to make that minus 33. And we'll come over here and make this one positive 33. And we're going to get rid of this y dimension, make that zeros. And now we've turned this into a vertical. So it's still the same length, it's 66 feet long, but now it's a vertical. And we're still in free space, so this should model out the same. SWR plot should be the same, and it is. Still at 71.71 ohms. And it's still a big ball of RF, but this time you can see the nulls are at the top and bottom and not on the sides. So this is a good start to modeling antennas. You just pick a wire length, you make sure you stick a source in the middle, Make sure that your segments are an odd number. In this case, I've got 11 segments. And that will allow you to put your source right in the middle of that wire. So we've got our source at 50%. We put in 50%. It actually is 50%. You can see right here it comes out at 50%, which, as we discussed in the last video, if we have an even number, it won't. So I just put 10 segments and that changed to 45. So if you're dealing with a wire where you want to put it right in the middle, you definitely want to use an odd number of segments. Now we're back to 50. So this is as easy as it gets, and we can put this above the ground if we want to. All we have to do is come over here to wire, change height, and let's put it a half wavelength above the ground. Let's make it 67 feet above the ground, and we'll change it from free space to real ground high accuracy. And we'll check the SWR again. You can see it looks almost exactly what we were dealing with, but the ground interaction has lowered our Z just a little bit. We're down to 68 ohms compared to 71 ohms. And when we plot it, now things start to change. Because of our ground interaction, we've got a much flatter pattern. And as I mentioned in the last video, I like doing 3D plots where you can actually see a 3D plot of what's going on. And you can also pull up an elevation plot to see what your actual gain at different angles is. So not a bad antenna. Okay, that's as easy as it gets. No easier antenna to model than a straight dipole. But our goal today is to model a ground plane. So let's look at a ground plane. So what distinguishes a ground plane are radials. And you can see here, your typical ground plane is going to have some number of radials, and they're sloped downward. Almost in every case, when you're dealing with a quarter wave ground plane, the radials will be sloped down. This is a Ciro, I'm not sure how you pronounce that, but Ciro ground plane that's adjustable between 27 and 45 megahertz. And you can change that resonance by loosening these clamps and just sliding those telescoping elements in or out to make that thing resonant on a pretty wide range of frequencies. And pretty little antenna. Not a bad price either, $75. But let's explore this in EZNEC. Why does the radials slope downward like this? Can we answer that question? Well, to start with, let's build one without sloped radials and see what happens. So this was a 27 to 45 megahertz antenna. Let's make this a 10 meter version of a ground plane. And for that, we're going to need a vertical element that's about 6 feet. So to start with, let's take it back down to free space. So let's change that, take that 66 feet out, minus 66, or was it 67, I think? Yes, 67. So now we're back down to the ground. And we'll change it from real high accuracy to free space. And we're going to make our vertical element 6.5 feet. So this is going to be 0 now. This is going to be 6.5 feet. Now let's add one horizontal radial to this at 90 degrees and see what happens. So let's put one radial in the x-axis. So we're going to start at the same point. So this point right here is 0, 0, 0. And then we're just going to make that x 6.5. These will remain zeros. So now we have one radial at 6.5 feet. You can see we have a problem with our source now. Let's take our source down to 0. That puts it at the base of the antenna. Now, you notice that the source will always be in the middle of a segment. And there are ways to change that. You can come over here and change the type of the source to a split source. And when you do that, that will effectively place that source at the junction of two wires. But in this case, we don't want to do that because we're going to be adding more radials at some point. So let's go back to that simple single current source. But it's not at the base of the wire. We really want it to be closer to the 0.0.0 point. So the way that we can do that is just increase the number of segments. You don't want to go crazy here because if the segment length is too short, it won't calculate current at the source point very well. So now we have a single radial, and the first thing we want to do is make sure that we're actually resonant at 28 megahertz. So let's shoot for 28.5, and we're going to check from 28 to 30, and only 0.1 is a megahertz frequency step, and run that. And it looks like we are short. So let's make this 7 feet. Actually, it needs to be 8.5 feet. That's why it's short. Put in the wrong numbers. So 8.5 feet. Looks better. Okay, so 28.7 megahertz. We're down to 1.2. And let's model it. So our free space model obviously is a little whacked up because we only have one radial. But the goal here is just to make sure that our radial length is the correct length. And now we're just going to add a few more of them. So we're going to come over here to create radials. And I just want to take 2 and make multiple copies of that around this antenna. Now, since that stereo antenna had 3 radials, let's just make it the same, and we're going to add 3 radials. Now these are horizontal radials. Remember that the stereo had sloped radials. Oh, we want to see what this does to our SWR, so let's go ahead and check it. And right off the bat we can see our impedance is quite low. 23 ohms. We're looking for a 50 ohm match to coax and transceiver, and this is 23 ohms. So there's your explanation of why these radials are sloped downward. Because if you remember, the vertical dipole had an impedance up around 70 ohms, which is it was a titch high. So a little bit high, and if we compare it to this, it's a little bit low. So what we want to do is kind of find a happy medium between those 2 points. So thus the reason for sloping the radials down. So how do we do that? Well, let's get rid of all of these radials. So zap, gone. Now we want to create a single sloped radial that's 8.5 feet. Now this can be difficult because when we angle a radial downward, the softwares are going to tell us its length. What we're going to be dealing with is a right triangle, so we'll look for a right triangle calculator. And Google happens to provide one of those for us. And what we want to do is find some numbers that will work and give us a C dimension of 8.5 feet. So if we have a 60 degree, roughly 60 degree downward slope, that will match that serial antenna. So we want our A dimension to be bigger than the B dimension. So let's just plug in some numbers and see what happens. Let's make the A dimension 6 feet. And let's make it 7 feet. and the B dimension 6 feet. That's way too long. We're at 9.21 feet, so let's change this to 6 feet and 5 feet. That's too much, so let's add a half a foot to that. And that's pretty good right there, 8.5 feet. So let's make our height on our radial 6.5 feet, and our distance away from the 0 Z point 5.5 feet. So 6.5 and 5.5 feet are going to be our dimensions here. Once again, 0.0.0 is where we're going to start. And then in this case, on our Z axis, we're going to be minus 6.5 feet. And then on our X axis, we're going to be 5.5 feet. Like that. And because we verified this with our right triangular calculator, we know this is 8.5 feet, which equals our vertical section. And we can check the SWR. And you can see we're a little bit too long. But let's try with that. Let's go ahead and create 3 radials. Not 2, 3. And there we go. So this is starting to look like our antenna from Stereo. Very close. Looks very, very similar. And let's check our SWR again. And it's pretty good. We're a little bit long. Let's go ahead and shorten it just a little bit. Let's scale this thing, and we're going to make it 0.99 of what it was. You'll see all of our numbers change. And we'll check SWR again. And we're still just a little bit long, so let's do that again. Scale. We'll make it 0.99 of that. And we're getting closer. Let's do that one more time. So 0.99. And that's pretty good. So 28.5. And look at our impedance. So by sloping the radials down, now our impedance is 53 ohms. So we're pretty close of ideal. And now what I'm going to do, before I model this, I'm just going to get rid of this extraneous decimal point to the right stuff. So I'm going to bring this over, make this 8.245, and we'll change this to 5.34. And there's a 0 in there, so I'm just going to get rid of that up to the 0. And over here we'll make this 2.67. And we'll just leave this at 4.62. We'll just take everything to the second decimal point to the right. And we'll double check and make sure that didn't mess up our SWR too much. It shouldn't have. And we're still good. And then we'll model it in free space. And once again, our nulls are top and bottom since it's a vertical. And now let's put it above the ground. Let's take it up 17 feet. And change our ground type to real, high accuracy. Model it again. And now with ground interaction, we have a nice pattern. When we see the 2D version of that pattern, you can see pretty good gain down low at 5 degrees, so only down 2 dBi at the horizon, so pretty decent. And pretty omnidirectional too as well. So there you go. modeling a simple 3 radial ground plane, not very difficult at all to do with EZNEC. So my recommendation is to start with a dipole, start with a horizontal dipole first, and then flip it vertical, and then try your hand at a ground plane. And you can make it for any frequency. We could scale this thing if we wanted to. So 10 meters, let's scale it by 4 and see if we can get it to work on 40 meters. So now look at our wire lengths, they're huge. See if it'll work at 7 megahertz. Nailed it, look at that. Perfect. And we'll plot it. And since we scaled it, not only did it lengthen the wires to work for 40 meters, but it also raised it above the ground by an equal wavelength height. So the pattern looks the same. It's actually identical. Gain numbers are very close too. So there you go. Our ground plane could be any size, but obviously you're not going to see too many of these with radials that are this length. So it would be difficult to construct and put something like this in the air, but it's not impossible. So there you have it. Simple ground plane matching a stereo antenna that you can get on Amazon. I'll put a link for this antenna in the comments. Looks like it's a pretty good one. And thanks for watching.